Dear friends, today we have with us one of Australia's eminent scientists from the Research School of Astronomy and Astrophysics at ANU, Dr. Charles Lineweaver. And Dr. Lineweaver is here with us to talk about NASA's DART mission, which seems something straight out of science fiction. Dr. Lineweaver, thank you so much for joining us.
You're welcome.
Yeah. Dr. Lineweaver, let's talk about this mission. I remember around 20 years ago, there were movies like Deep Impact and Armageddon. And at that point of time, this stuff seemed like science fiction at that stage, but NASA has actually executed this mission. So can you tell us more about the DART mission and its significance?
Right. The DART mission, DART, stands for Double Asteroid Redirection Test. So it's important for many listeners to know that it's a test. This asteroid has no probability of hitting the Earth, but it is a test to see if we humans can, if there were something that's going to hit us, if we could redirect it. And this is called a planetary defense mechanism. It's based on, we have found an asteroid called Didymos, and it has a little moonlet going around it once every 11 hours and 55 minutes. And this is about as big as a football stadium. It's 160 meters in diameter. And this one is almost a kilometer. And it's going around, it's a kilometer away, and it goes around 11 hours and 55 minutes. And what the idea is to have a spacecraft hit this one, boom, at 6 kilometers a second and slow it down. When it slows down, it will get closer to the center asteroid, and then we will measure how much we have redirected it. I should say that this spacecraft is only about half a ton, and the asteroid, the little moonlet, is about 5 million tons. So there's really just a tiny, tiny thing hitting fairly rapidly into a large object the size of a football stadium, or the size of a pyramid, for example. I was just in Egypt, so it's about the size of the big pyramid in Giza. So, but the whole point is why this is the first mission we've ever tried to protect the Earth from an incoming thing, but it's not an incoming thing. It's a test, as if it were incoming. So it's humans defending ourselves from a potential threat, which we know was there because 65 million years ago, there's a large object about 10 kilometers in diameter that did hit the Yucatan Peninsula and essentially wiped out the dinosaurs, leaving birds and mammals to take over. And this is something that happens periodically, but million years or 10 million years is the time scale, not a human lifetime. So during our lifetime, it's very unlikely that any big threat will happen. But in 1,000 years, 10,000 years, the probabilities build up, and we want to be ready, and we hope that we will last that long as a species.
Dr. Lineweaver, when are the initial results expected, whether the test has failed or has it been a success? And is there any indication so far, because this happened, I think, just some hours ago, what is the outcome so far? What's known?
Well, the outcome so far is that the mission to hit the asteroid was a tremendous success. It hit exactly right in the middle of the thing where they wanted to do. Now, I should point out that I think about 10 minutes before the impact, the whole thing became automatic. So the satellite was constructed so that it would no longer be adjusted by human beings for the last 10 minutes before impact. And that automatic targeting seems to have worked perfectly. Now, the reason why this was done is, and the reason for the big uncertainty is, we don't know much about the density and composition of these asteroids. And that's something, if we want to redirect something, we need to know that. So why is that? For example, let's suppose that this is the thing that's being hit. If it's kind of amorphous and like a cotton ball and it goes in, well, then it will not make much of a splatter. And that splatter acts as a little jet to redirect it. But if it's really hard, then it'll go boing, and then things will jet off the back, and that will redirect it even more. So the amount by which a certain satellite of a certain weight at a certain velocity hitting something will redirect that something depends on the composition, and that's something that's a large unknown, and that's probably the uncertainty that will be reduced. We haven't reduced that yet. And you asked about what is the result so far. The
Mhm.
result so far is that it's a direct impact, but
Mhm.
we have not gotten the main result, which will be how much will this moonlet, how close will it come to its asteroid that it's circling around? And that will tell us how effectively the redirection has been. And that effectiveness will depend on the composition of the thing it hits. That's why there's uncertainty. The bottom line is this thing goes around 11 hours and 55 minutes. Maybe next week we will find, now the orbit is 11 hours and 45 minutes. So we
Mhm.
will change the orbit by about 10 minutes, maybe even 20 minutes. Now that's a large uncertainty, but that's the kind of thing that scientists will find out in the next week. Maybe it'll take next week we'll have a maybe a 1 minute precision, but maybe in a month we'll have a, I don't know, 10-second precision on the orbit. And that's just, science. We're getting more and more precise. And that's because when it hits, it makes a big dust ball and we can't really see exactly where the thing is. Probably it'll take maybe, I don't know, maybe a couple of days for it to clear out. But there is a CubeSat that was launched away from DART about maybe, I think it was 10 days ago, so that it would pass by and have a look at the impact site to see how much dust there was and to see how effective the thing was, where exactly it hit. And that's
Mhm.
an Italian CubeSat, which will take those pictures. We expect those probably very soon, maybe in the next couple of days.
Yeah. Dr. Lineweaver, now this mission potentially could have historic significance for the survival of humans, for the survival of our species. Can you briefly explain why this is so important in terms of asteroids? Because in our day-to-day life, this is not something that most people would think about. But there is always this potential danger of any asteroid or any other thing coming and hitting the earth.
Yes, we have put up a lot of satellites into low Earth orbit, and when they lose control, become uncontrolled, they spiral out of control. A lot of them get burned up if they're small, but if they're large, then they hit the Earth. But usually the Earth is not very populated. If you look at the Earth from outer space, only a tiny, tiny fraction is where people are.
Mm,
And but if you get an object that's 100 meters or 200 meters or a kilometer or 10 kilometers in diameter, the bigger it is, the more dangerous it will be. And like I said, the 10-kilometer diameter asteroid that hit the Earth 65 million years ago wiped out many, many, many species. And we would probably, if we were around then, we would have been wiped out too, I suspect. It's only our ancestors that were hiding in holes and had lots of fur that were able to survive that. I doubt that humans would be able to survive such a thing. But that is very rare. That's something on the order, like I said, 100 million or 10 million years.
mm,
However, if you go up at night and look at the sky, you will see boom, boom, boom. And these are tiny pieces of sand that are hitting the upper atmosphere, and we call them shooting stars. But there
mm,
are also objects this big in my fist, and and they're a shooting star that lasts a lot longer. And some of
mm,
them are this big as my head. And so there's a whole spectrum of different mass objects. And the
mm,
smaller the object, the more numerous they are. And that's why you can see every night some shooting stars, but you don't see every night a big blazing across the sky. That would be something the size of your head or your body. And this object that was redirected was at about 160 meters in diameter. So that's kind of like the small end of the things that can really do damage. If it hit, for example, in a city, for example, it would do quite a bit of damage. But things less than that they're harder to detect. And so up until now, we've ignored them. Right now, we're concentrating on trying to know way ahead of time where the biggest things that might hit Earth are. And so far, you should be able to sleep very well, and probably your grandchildren as well. But who knows? Sometime, maybe in 100 years, we will find something that's 2 kilometers in size coming at us from a direction that we cannot monitor. I should point out that if this asteroid comes at the Earth from a direction that's not towards the sun, we can see it and we can detect it, maybe even a year before it hits the Earth. But if it comes from the direction of the sun, it's very hard to see that coming. And that's why the requirements for, Congress and something called Space Guard tries to get 90% of all the objects that could threaten the Earth. And it's the reason it's not 100% is exactly because some objects come at us from the direction of the sun, and that blinds our telescopes and makes it very hard to see them coming.
Yeah, and also, of course, there are objects falling into the Earth's atmosphere very often, and most of them, get burnt in the atmosphere. So, how big would an asteroid have to be to cause serious damage? Whereby something like this mission is required to deflect it.
Well, because we're pretty precise on where something will hit, if this object, let's say we have 100-meter diameter object, and if that were going to hit the Earth, we could probably figure out where on Earth it was going to hit. And if it was going to hit in the, I don't know, the North Pole, the South Pole, or some place that very few people live, we probably shouldn't even bother to redirect it, because it's very little. I guess it would not cause that much problem. But if it gets to be a kilometer or maybe half a kilometer, that's a much bigger deal. On the other hand, objects that big are much rarer, much less frequent. So the bigger they are, the more dangerous they are, but they're much less common. And so that's the game we're playing. And they're easier to detect as well. So the little things we don't care that much about, they're hard to detect. They hit the Earth all the time. But when they start to get bigger, that's when they get easier to detect. They get more dangerous. That's the ones we're looking for. And so basically, we astronomers are doing our bit to try to protect the Earth from these objects that hit in outer space, that come to us all the time from outer space. We're looking for the big ones. Those are the ones we need to be concerned about. So far, we haven't seen one that should keep you up at night. But this is kind of like the first mission to protect the Earth from such objects.
Yeah. So potentially there's the size. If it's a larger object which which is an area of concern, and then with the smaller ones, it also depends on where it might hit. Say if it's falling into the ocean, then it may not be of that much concern. But say if it's going to land into like a populated city, then it might be something that could be considered worth deflecting.
Exactly. And there's all kinds of ways to deflect them. Today's mission, the DART, was to hit it and then redirect it. But if you detect something far enough away, let's say it's going to hit the Earth in a year, well, then you could maybe even paint one side of it. And then that would cause the sun to reflect the photons more in one direction, and that would redirect it. Or you could try pulling on it. There's all kinds of ways to redirect an asteroid, particularly if you have enough time. It's really, really important in these issues to detect it early, and that gives you maybe even 5 years time. But if it's only a couple of weeks, that's much harder.
Yeah. Dr. Lineweaver, what are the kind of technical challenges in planning and executing a mission like this? Because in space, a 1 second anomaly could, make the mission fail, because there is, things are traveling at such huge speeds, such high speeds. So it's really, even a second of delay here or there can change the mission's course entirely. So how difficult is it to actually plan this kind of a mission and execute it?
Well, you're right in saying that seconds matter, but the positive side of that is, if here's the Earth going along and here's the meteorite might hit it, but if you delay this by maybe even a second or two, it could then miss the Earth because you've successfully changed it a tiny, tiny bit, but that changes it by a couple of seconds, and that could make it miss the Earth or make it hit a part of the Earth that is not inhabited by that many people. So yes, it's a precision science, but that precision science works in both ways for the advantage. All you have to do is change it a tiny, tiny bit. If this asteroid is going to hit the Earth and it's 5 years away, you can just push on it, go boop a little bit, and then it will not hit the Earth anymore. Why? Because this little push adds up and adds up and adds up, and then it will miss the Earth.
Yeah, and it's really fascinating to think about it in that way, that just a little nudge has the potential to save humanity if it ever comes to that.
if you get it early enough.
Okay. All right. And just finally, one last question, Dr. Lineweaver. Do you see many more missions now on these lines going forward? That this is just the first, but once we get the results and as we move forward, that this is an area which actually is requires our concern, because we never know what might be coming our way. And of course, we have satellites, and we can look into deep space, and we can probably detect objects that are still a bit far away. But do you reckon that we are going to have more missions on these lines going forward?
Well, yes, there are two approaches to this question. One is, for example, in 2 years' time, Hera, a satellite that's going to be sent by the ESA, Europeans, is going to go to visit this system, Didymos and Dimorphos, and it's going
Mhm.
to look exactly where was hit and get a much more precise idea of how big the hole was, what kind of splatter occurred. So that's
Mhm.
one thing. Yes, there are missions in the future, and that's a particular one. I think the probably most effort should be spent in the next decade in figuring out better telescopes to identify these objects while they're still very, very far away. And like I said, we have a good census of near Earth objects, but it can be much better. And here's the thing that's most important. When you find an object, an asteroid that's going around, and you say, okay, I know how fast it's going, I know how far away it is, where will it be in a year? And then you look and say, oh, it's not exactly where I thought it was. Oh, what did I forget? And then you correct the physical phenomenon that you've forgotten to put in. Maybe it's rotating more slowly than you thought, or maybe it's reflecting the albedo, how much sunlight is reflecting. There are all kinds of small effects which add up over time that make the prediction of the trajectory of these things difficult. And we can get much, much better at that by tracking many, many thousands of such objects. And that's what we're starting to do now. We will continue to do that, and our computer trajectories will get better and better. And so I'm pretty optimistic that we will be able to protect ourselves if we can live with ourselves for about 1 million years or so. I think that because of this is a technological problem that can be solved, unlike, I guess, war, pollution, climate. Those things seem to be, we're going to kill ourselves probably before the universe kills us.
Dr.
On that
Charles
optimistic
Lineweaver.
note,
Sorry.
thank you very much.
Thank you so much for joining with us. Thank you so much.
You're welcome.